Okay, so good afternoon, everyone. Thank you for joining us back from lunch. We have an interesting session now, and the first speaker is Reut Tsarfaty from the Open University. Actually, me and Reut goes back a long time. We met in Amsterdam when I was doing my master's. She was doing her PhD. After that, she had a postdoc position in Uppsala University in Sweden, and then she worked with David Ariel in Weizmann Institute on various topics regarding like syntax and statistical parsing, etc. She got quite a few research grants, including the ISF and the ERC. And without further ado, Reut.
Thank you. Hi, everyone. I'm Reut Tsarfaty. Thanks for the kind introduction. These days, I head the NLP Lab. This is the Open University Research Lab for Natural Language Processing and Artificial Intelligence. And what I'm going to talk about today is a topic that has been occupying us for, in fact, quite a few years. And this is a very basic question about NLP. What's wrong with Hebrew NLP? Why doesn't it work as well as NLP for English and French and Swedish and many other European languages? So I'm going to talk today about why doesn't it work very well and also how to make it right. So let's start with what's the essence of NLP. And the essence is, I think most people here would agree that what we really want to do is to take unstructured texts that we have, and we have a lot of them, from social media, from business documents, or what have you, and to turn them into structured insights. These insights can be in the forms of structured tables, some forms that you want to capture the information. It can be populating knowledge bases or databases with information that you need. Or it could be developing digital assistants, right, like Siri and Alexa and Cortana, something that will understand what you say and then be able to execute this or perform some actions in response. And the big secret of this little magic that happens in this innocent error is that this NLP component is in fact a quite involved pipeline. And this pipeline has different levels of analysis. A basic level of analysis, which is analyzing the words. So with this sentence, the quick brown fox jumped over the lazy dog. We have nouns, right, fox and dog, and we have verbs, and we have prepositions like over, etc., etc. I may want to be able to identify the entities in the text. Here there are no named entities. I may want to look at the syntactic structure of the sentence. This is who did what to whom. This is something that will help us understand exactly what's the events that are talked about. And there are deeper levels of analysis, something like a co-reference resolution. So I want to know maybe that this his anaphor refers to the president of China visiting the United States. And all of these components provide increasing level of abstraction in order for the structured insight to be represented in a structured form and be used for further applications. So this particular pipeline that I'm showing here is the Stanford Core NLP package that some of you may have heard of. Many may have worked with Spacey. This is another NLP pipeline which is very successful. The third logo that you see here refers to UDPipe. UDPipe is a similar pipeline based on neural networks trained for over 80 languages. And it works also for Hebrew. But if you try to parse Hebrew using these pipelines, what you get for a very simple sentence, like Ganan, Gidel, Dagan, Bagan, right? What's the verb here? Gidel, I think everybody can tell that. So UDPipe thinks that Dagan is the verb. In fact, it thinks it's digen, if you look at the binyan over there. It thinks that Ganan Gidel is a proper name, like Reut Tsarfaty. It thinks that this noun is a construct state, which you don't see here because you don't see the features. So if you go on the UDPipe web page and you try to experiment with different Hebrew sentences, you see that it's really not good. And it's the same technology that works very well, not only for English, but for a range of different languages. So what goes on here? And what goes wrong here, really, is that in Hebrew, you really cannot trust the words. And what I mean by that is that if you get a single word like this one, what is it? Yeah, it depends what you've done in the break, right? If you already had your coffee, maybe it's coffee. If not, if you were talking about Bereshit, right? Maybe it's an orbit that you're talking about. And if you're talking about the orbit, then it's a noun. And if you're talking about the coffee, then it corresponds to two different words in English, right? The coffee. And if you have our favorite example in the lab, this four-letter word, it has very different analysis that you can have. It can be the organization, B'Tselem, or their onion, right? Batzal Shelahem, or in their shadow, Batzel Shelahem, or in the photographer, right? It's not there, and all the different analyses are in this single picture that my student Yochai was drawing at one day. So you can see that this extreme, what we call morphological ambiguity, is really bothering. And the only reason to resolve it, even for humans, is to know in what context you are. So if you have Irgun B'Tselem Itria, you know that this is a noun. And if you have Yoshavnu B'Tzilam Anaim, you know that you have to consequently segment it to different items and assign different part of speech tags, different syntactic structure, and so on. And this creates a loop for every application in Hebrew. So if you have some sort of application that you need to provide a syntactic or semantic analysis, you need to first know the morphological analysis, how to perform the segmentation into words that will correspond to words in English, right? But in order to do this, in order to do the morphological segmentation, you must have the context. The context comes from syntactic or semantic analysis in your domain, in your application. So this creates like an egg and chicken thing. What can you solve first? And if you don't solve one, you cannot solve the two. And this is the problem. This is the problem for every NLP application that you have, and this is one problem that we are looking at, how to solve it for dependency parsing. Okay, so what do we do? Or actually, what do people do when they get texts in Hebrew? So what many people do, researchers and in the industry, is take the approach of simply pretending Hebrew is English. And it's done a lot, more than you would think. So every time you hear something like, Bert was trained on Hebrew, or we have word-to-vec embeddings published on this website for Hebrew. This is pretending that Hebrew is English. So not doing anything to the input stream, just taking the spaces to delineate the words. And this creates different and not very predictable behavior for these vectors that may go into your applications. Sometimes it's okay, it really depends on the task, but if you have a task like dependency parsing, and you haven't broken down B'Tzel into two items, you can never get the correct parse tree. You can never see that the preposition is actually attaching into a modifier, and you can never know the semantics of this actual sentence. So that's not the best approach you can take. And people in NLP researchers know that for about a decade, since the Cornell shared task on the dependency parsing. So what people have started to do about a decade ago is to make Hebrew look like English. This means that we have an MD component, a morphological disambiguation component. We take a morphological decision. We decide which morphemes are in my input stream, and then I pretend that it's English. And I continue to work with the stream with the similar application as we do for English. This is, again, okay for some applications. But what we've seen before with UDPipe, with Ganan Gidel Dagan Bagan, happens because of this approach. So UDPipe is a pipeline, tries to make the morphological decision, makes many errors because it doesn't have a wide context, and then when we get to the syntactic parser, we just cannot recover from the error. So that's a very extreme error that's lingering to the NLP component, no matter how great the technology is. And when it comes to the business application downstream, then the precision is really not very high. It's not very useful for practical use inside the application. So what can we still do? Well, we can try to solve these things jointly. We can understand that this is actually one task when we have to solve the ambiguity at the morphological and the syntactic level, and write the one single objective that solves it. And that's great. Actually, theoretically, it sounds like a good idea. The disadvantages of these are that it requires research. It requires time. It usually cannot be done in the context of a business organization or some startup that's on the run. And we are doing it so that you don't have to. So let me just, in the remaining part of the talk, really show you what we've done at the lab, how it looks like, what it can give you, and actually you can go home and quite immediately start playing with it. So let's start with more formally defining what is the task that we are now redefining. So we're sort of dropping the pipeline conception altogether, and we have a single objective function where the input for the objective, the input is a sequence of Hebrew tokens. Tokens are the word space delimited as they appear in the, say, newspaper or just natural data. And the output Y is a morphosyntactic tree. What is a morphosyntactic tree? Let's make this a little bit more precise. When I have a sequence of tokens, I can construct what we call a lattice, the morphological analysis lattice. And this word B'Tselem that we just cited a few slides ago has very many different ways in which it can be decomposed into morphemes. And every path is a possible decomposition. And if you look at the single arc in this decomposition, I don't know if you can see from there, this cell, this is transliterated. This is a morpheme which corresponds to a noun. And we have morphemes that correspond to verbs and to prepositions and adverbs, and the same sort of range of word units that correspond to what word would mean actually in English. So this space embraces the ambiguity. It doesn't try to solve anything, just represents this is the space of analysis that are possible. On top of this lattice, every arc can serve as a node in a dependency tree. A dependency tree is a set of arcs indicating the syntactic function between every sort of pairs of words in the sentence. So we have the pair that defines a subject relation, and the pair that defines an object relation, and so on. This is useful for further semantic applications. And the third space looks like this. We have a lattice. Each path in the lattice is one possible morphological decomposition, which then can accept an exponential number of dependency trees. So we have multiple paths with exponential number of dependency trees over each one of the decompositions. And we want to select one pair that has the morphological decision and the syntactic tree, the syntactic decision. They should correspond to one another, and they should represent the most likely analysis of the Hebrew sentence as a human would depict it for you in context. So that's our goal. And if you got this slide, you basically got the whole thing and enough to continue it. But I'm going to specify a few of the details that sort of happen behind the scene there. So this very simple expression represents how we construct this algorithm. We have a generative component, the transition system, that actually creates the different candidates, the different passes in the lattice and the different dependency trees. It keeps making suggestions, so to speak. We have the argmax component, which is the beam search decoder, and we have a score. So score Y gives a score to every morphosyntactic pair of every morphosyntactic analysis. Now, we will not be able to go really deep into the detail of how to define a transition system, which has to be different than how we define transition systems in English. In principle, we have what's called configuration. That's basically the lattice and the path I have so far. And at every point in the lattice, I can start to make a morphological decision, which kind of action I'm going to take. And the beam search decoder picks K actions at every point to continue with. And after several decisions, we get into a point where the word ends, and we continue with the next words in the sequence. The configuration, the generation of candidates in the dependency parsing side is really the same as is done for English. So once we have morphemes, we can use a stack and a buffer like people do for English and construct tree with a transition-based arc-eager or arc-standard, which are usually used for English dependency parsing. The beam search decoder acts in a way that at each point we expand all the possible actions. So we create all possible candidates with the range of actions that we have. We select the top K according to the score and continue to apply actions. And each action gets the score that is being trained using the structured perceptron. The only difference from standard perceptron that you may be familiar with is that, so we iterate over the example, we predict, and if we fail, we need to update the date. What does a failure mean? A failure means that our candidate fell off the beam. So we lost the best candidate. Our objective is to keep the pair, the best pair, inside the beam all the way through the end of the analysis and get high score. And this is how we train it, and this is how we make sure that the morphosyntactic analysis gets scored to be promoted as our best candidate in the end. So the hypothesis is that it will work better than a pipeline. We can implement both a pipeline and a joint system with this, and we check it. And what we actually see, so this is implemented from scratch. The parser is called YAP, yet another parser. We use the wide coverage lexicon from Mila in order to create the morphological analysis lattices, and we have about 5,000 sentences for training with the rest for validation. That's really not that much. And we report our labeled and unlabeled F-scores for both morphology and the tree. And what we see, to make it short, is that really when we run in the joint setup, both the morphological and the syntactic components work better than if they would run in standalone or in a pipeline scenario. And what we also did, and you can read about it in the paper because I will not have time to go into that, is that when we check our parser in the settings of other researchers in their own setup, we really perform significantly better. So this is the work from Goldberg and El-Haddad into 2011, and there was work on joint parsing for Turkish in 2015, and we are also in their setting perform significantly better than them. And we also did some qualitative error analysis to show a really drastic decrease in the errors that we see. So if we have annotation errors, we make the same kind of errors as any other system. But if we move from pipeline, from joint, we just had almost 50% drop for the kind of errors that get from the morphosyntactic mismatch. So it does exactly what we expect it to do. And instead of talking further about it, what I'm going to end the talk with is really showing you how this looks like in real life. And I think we're going to start with our gardener, Ganan that grew grain in the garden. The moment it gets changed into Hebrew. Okay. This is an online demo that we have for the parser. What you have is just this window, and you click Submit. And the first thing you get is the segmentation, right? So, Ganal, Gidel, Dagan, Behagan. Note that in Hebrew you don't always see hey, the definite article. It gets sort of swallowed by the preposition. You can also see that the part of speech tags are correct. We have a noun, Ganan, gardener, a verb, Gidel, grew, a noun, grain, and in the garden, preposition with definite noun. You have the lemmas, you have the morphological features. So you can see that Ganan and Gidel are both masculine singular, right? This is the grammar of Hebrew, and statistically we find that indeed the gender and number of the subject and predicate match. And we also get the syntactic parse tree, and it's completely correct, right? As you would expect, Gidel is the predicate. You have a subject, Ganan, and an object, direct object, Dagan, and a prepositional modifier. What else we get here, and this is interesting if you want to look at it, is the space I was talking about. So initially I told you there's a huge space. We're talking about actually 4 words, and this is the space of analysis that are possible. So this explains why such a simple sentence doesn't get parsed well enough with UDPipe or with Stanford Core NLP. But if this ambiguity is self-embraced and you put it into the inference and you make a joint decision, then you can actually get very good accuracy even with only 5,000 sentences. No word embeddings, no anything. Okay, so let's go back to our slides. What's left to do? A lot, right? So this is just the beginning. We have done some work on sentiment analysis. We are going to release, probably in the coming year, also a named entity recognizer that uses similar ideas. We're starting to work towards information extraction, co-reference resolution. Everything is online on the website. You can freely use it. It's open for you. And what I just want to end with is say that Hebrew NLP is challenging. It's difficult, but it's feasible. If one does joint modeling, then you get really good accuracies. And if you have to or want to work on Hebrew applications in AI, in data science, or any sort of language technology, do that. Do that, and if you meet certain bottlenecks or needs, tell us, and we'll work further to make it better for the entire community. So thank you very much for listening. Mm-hmm.
But if I want to use BERT, for example, for question answering, can I use your output of the parser in order to give him other features? Because right now I just need to give him the tokenized text. I don't need to give him anything.
So first of all, thanks for this question, because this is what most everyone is doing today. Just use BERT as is. So the one take-home message from this talk is that you work on units that are of different granularity. So on one hand, if you use this, you decompose the words into morphemes. This is better probably for your application. On the other hand, BERT was trained on tokens that have not been tokenized. So I can tell you two things that we already do at our lab. And I can, so in the named entity recognition scenario, sometimes even if you use the actual tokens of, say, let's talk about fast text, and use them with the morphemes, that already works better. Because if you've seen met Thailand and let Thailand and so on, it will only pick up Thailand, the morpheme that you segmented, and you'll have a good enough vector for that. So actually, already by replacing the units that you analyze, you can get better in your application. But that's not perfect, because what we really want to do is retrain these models, like Glove and fast text, for these morpheme levels, and we do that. But with BERT and Elmo, as you probably know, they use context, and context is indeterminate because it's in the lattice. So you don't know where you came from, and you don't know where you're going. We have research towards solving this too. It's too premature to tell you about it, but I'm hoping that in 1 year we'll already have the methodology to actually inject the feature that you want from something like BERT into something that does sort of sophisticated analysis and still retain the accuracy. And we're all hoping that's to come, relatively soon. Thank you very much.